Greetings and welcome to my new calculus channel. My name is John Gabriel, and today I want to discuss a very important topic with you once again, a topic that has been ignored for quite a while, and it just seems that the more evidence I produce for mainstream academics, the more they believe in their fraudulent formulation of calculus. So let's begin. Now, what you see here in this red box is an identity that is provable from my historic geometric theorem discovered in January 2020. So what it tells you basically is that the slope, where I'm pointing to, of the non-parallel secant line is equal to the slope of the tangent line plus the difference. Okay, q of xh is a multivariate function which stands for the difference. And all this is proved in my articles, to which I shall place links once again in the detail section so that you can see. And we can see in this very one slide why the current formulation of calculus is a fraud. So we know that the limit of this finite difference is what the mainstream academics consider to be f prime of x, or the slope of the tangent line. Now, if that's the case, then we could substitute this expression here in terms of the finite difference on the right-hand side. But it turns out that the limit as h approaches 0 is actually irrelevant in this case. Why? Because both the slope of the tangent line and the difference between the tangent line slope and the non-parallel secant is constant. Okay, so these two values here are constant. So it turns out that the limit of the finite difference is equal, which is equal to f prime of x, is equal to f prime of x plus q of xh, which is only possible if the difference is 0. Now, there's one case, and one case only, when that is true. Can you guess? The straight line, that's right. So if we have the straight line, we can really just omit this limit here, because then this difference quotient is equal to the slope of the tangent. Well, it's not really a tangent line because it's just a straight line that you're dealing with. It's rise over run, right? So, okay, so let's get rid of that and let's take a look at why mainstream calculus is a fraudulent formulation. So we see that the derivative is defined as this limit, and we know also from what I've just told you that this finite difference is the sum of two slopes, or the sum of a difference and the sum of the tangent line. Okay, so the difference is really just the secant, the non-parallel secant line slope minus the tangent line slope. And you can see the proof of all this in the article that I'm going to put in the detail section. So both f prime of x, and we didn't have to call this f prime of x. We could have just said up here that this difference quotient is equal to, we could have written this out. We could have said non-parallel secant line slope is equal to slope of tangent line plus the difference between them, right? Okay, so since both of these slopes are constants, we have that f of x, as you see here, is equal to f prime of x is equal to f prime of x plus q of xh, which is possible if and only if q of xh is 0. And this only happens in the case of a straight line. So the first law results from taking the limit of a constant. Okay, what is the constant? These two here are the constant. Now, q of xh is a fixed value for any x and h. Okay, so depending on which your x is or what your h is, there's going to be a corresponding slope of the tangent line and a corresponding slope of the difference. So this doesn't move or go anywhere. It doesn't go to 0 or anything like that. That's just nonsense. But it can, so what we're saying is that if we throw Q of XH away, it means that this identity is false. But it cannot be false because it's realized from a proven theorem, okay? So if f is a straight line, then this here is 0. And that's the only time that it's 0. So to discard Q of XH implies that this finite difference quotient is equal to f prime of x, which, as I said a few times over, is true only if f of x is a straight line. So now this epsilonics definition that you learn in a first semester course of calculus, it actually uses a derivative because this L here is already what you were supposed to get from this limit, okay? This limit here means this expression up here, okay? So this limit here means this expression here. So it's circular. Why is it circular? Because L is equal to the derivative at C. And that is what this here is intended to give you. So we could rewrite the mainstream definition slightly better by replacing the h with w over n and taking a limit to infinity rather than h to 0 and letting h equal to w over n. But we'll still have the same problems as the original definition. So for example, we know that the finite differences converge to some value, and we can see that the most important finite difference, which is the one at the point of tangency, is always undefined, okay? So the above definition that I gave you here, this definition, never assumes the form 0, 0. But even if you had an infinite task, hypothetically, because there's no such thing as an infinite task, it would be insufficient because there is no n such that w over n equals to 0, okay? In other words, they both suffer from the same problems. And I've shown you at least 2 major flaws with many other questionable techniques that are used in the mainstream calculus. So I encourage you to download my free ebook and to become a subscriber if you're not already a subscriber, and to share the news of this channel. And hopefully I'll be able to chat with you again soon in the near future. My name is John Gabriel, and this is a New Calculus channel. Till next time, goodbye.